In motion part 2, we're going to keep covering 2D motion, which is projectile motion for the most part. It's what we're going to be talking about. We're going to talk about Newton's laws of motion. We're going to look at orbital velocity, escape velocity, so you have an idea what those are. And we're going to look at friction and drag. And so let's get started with projectile motion. Well, when we add gravity into the mix, what's happening in this problem? Remember, x and y are independent of each other. So in x, we just have constant velocity. Whatever velocity you started off with in x, you still have. Now, we're ignoring air resistance here. You still have that velocity in x. In y, it's like the guy throwing the ball up and down. Right? In y, you have an initial velocity up, and you're decelerating downwards the whole time. You come to a stop, and you head back down. So in x, we've got our constant acceleration equations, and in y, we have the accelerations with gravity in it. Minus 1/2 gt squared v naught yt plus v naught plus y naught, right? And so we're going to be looking, these are separate pieces. Now, you can put them together and calculate the range. That's going to be a discussion question for you guys to kind of work out how do you get there. But you're gonna have to derive that, by the way. So here you go. We've got gravity in the mix. We have some initial velocity v naught that's 30 meters per second at 45 degrees. Well, we have to break that down into the x piece and the y piece, or the x piece and the y piece, right? X, y. We have to break it down. If we don't break it down, we're doing things wrong, right? And so we break it down into its pieces. So now our x equation has the x piece of the velocity in it. And if this wasn't 45 degrees, let's say it was 30 degrees, we'd have 30 degrees in where the 45 degrees is. And so now we have these equations for this specific problem we're talking about at 30 meters per second. We could also do it at 40 or at 50, but there's the problem we have. If in this, we're going to ask the question, when does y equal 0? Now, there's the trivial answer, y equals 0 at t equals 0, because you start off at y equals 0. But then the other one, you have to solve for it. And you do that when you have this, right? Minus 1/2 a, okay. So the initial position, let's back up a couple of equations. Let's go to here. Because this is 0 right there, all right? Because that's 0, when we get over here and we're saying, okay, when is y equal to 0? Well, there should be a t squared here, and there should be a t here. But that's the trivial solution, t equals 0. So we divide through by t, and you're left with just a single t. And now we know the time at which this ball, this projectile, hits the ground. All right, goes up, comes down, hits the ground. And that's how long it's in the air. What's happened in the x direction in that time? Well, if you want to know how far it's gone, you have to go back and you have to put in that time into the x equation to get how far it's gone. And that's how far downrange it is. That's not its path length, which is a more complicated integral. You know, the path length that it actually traveled is longer than its range, which is how far it went in the horizontal direction.